So on this channel, we cover a whole wide range of different stories when it comes to renewable energy, clean cars, clean technology. Obviously, we do focus on electric vehicles and electrified transportation, but we also occasionally do cover renewable energy stories. And tying all of that together is battery technology. Now, we have some stories that do really well on the channel and some stories that don't do so well on the channel. So if a story is about a Tesla, it's generally going to get a high viewer count. If it's about an affordable new electric vehicle, it will generally get a high level count. If it's one of our Sunday musings, I know that they don't have as higher a view count, but that's okay because it's a Sunday video and it's kind of chilled and laid back. Sometimes you get videos that I think are going to do really well that do really badly, whether it's because the topic's not right or people just aren't feeling it. But I can tell you one video that always does better than any other video on this channel, and that's videos about battery technology. For some reason, battery technology videos just go completely off the charts, which is why I'm kind of excited to be making this video, because I know it's going to have a high view count, but also because of the guy that I've got with me to talk about batteries. Now, when it comes to electric vehicles, there are plenty of people who know a lot about electric vehicles, not so many that know about batteries. This guy knows about both. Please welcome Ewan McTurk from Plug Life Television.
Thank you. But it was 2009 that I first managed to get behind the wheel of an EV, and I didn't choose the Plug Life. The Plug Life chose me. So I was just about to go into my honours year of my undergrad degree in an applied physics degree called Renewable Energy at the University of Dundee. I was trying to decide what I wanted to do with my life. I knew I wanted it to be something interesting in the green sector in general, but what exactly? And then lo and behold, this 1999 Peugeot 106 electric pulls up next to me when I'm walking through campus one day, and it turns out that the university had just acquired it. So I pestered them every single day until I got to do my honours project and then my master's project on it. And that's what got me into it.
So let's talk about the car for a real quick second. So the Peugeot 206 is not
106.
106, sorry.
Yeah,
Peugeot 106 is not a car that many people knew was electric. I mean, I was familiar with it, but so it was a limited production vehicle, a compliance car, and it didn't use lead acid batteries, did it? It didn't use lithium batteries.
No. It predated, almost predated Lithium-Ion. Lithium-Ion was 91, 92 that first came out in, I think it was like a camcorder or something like that. Still very much in the consumer electronics stage. But PSA Peugeot Citroën produced 10,000 nickel cadmium electric vehicles between 1995 and 2005. Most of them were left-hand drive. Most of them were in France or across continental Europe. A few of them were right-hand drive and made it to the UK. Then most of those were repatriated and crushed, but some of them slipped the net, including the two 106s that I owned at one point until I decided that's a bit silly. I just need one, really. So, I mean, they were surprisingly robust, reliable machines, but there was a bit more maintenance required because it was a so-called flooded battery. It needed to be topped up with deionized water every now and again. And I mean, it predated any modern charging infrastructure. So it was only ever charged using a 3-pin plug. It had we'd never heard of J1772. We'd never heard of Type 2 or anything like that. So it's not compatible with modern infrastructure, but it's still a fantastic wee machine to drive.
And I've actually had the pleasure of driving one. It was quite an experience, and it's a good reminder that electric vehicles, we think of electric vehicles as being a new thing. They've been around for a really long time. But while I could talk to you about electric vehicles that you've owned for a really long time, that's not why I've got you on here. I've got you on to talk about the breakthrough battery that we covered more than a year ago now on the channel, JB Goodenough's glass battery. It hit the headlines. It was a phenomenal news story. It, I think, is probably one of our highest videos ever. And for those who don't know, JB Goodenough is considered the father, or one of the fathers, of the lithium-ion battery. Actually won a Nobel Prize for it, for his work on lithium-ion batteries. And modern electric car battery packs wouldn't be around if it wasn't for the work that he did, as well as some of his colleagues in the field. Each of them did a little bit of different work that actually led to the ultimate ability of chemists, electrochemists, to build the lithium-ion battery. But you've hinted that you've been to university and you've done a doctorate. You started off with physics, but now you're an electrochemist, right? And a mechanical, electromechanical degree.
Oh no, electrochemist. So
Electrochemist.
yeah, it was an applied physics degree that I had as an undergrad, and then conveniently, the University of Dundee's just across the River Tay from St Andrews, where at the time one of the biggest and most well-known battery research groups in the world just happened to be based, Professor Peter Bruce. I'd studied lithium air, which at the time was the poster child of modern battery tech, this up and coming thing that was only 5 to 10 years away, and 5 to 10 years on still is. But yeah, so I did my PhD in that. Then the group relocated to Oxford. So I've been to Oxford. Yeah, I don't like to bang on about it, but I've been to Oxford. Yeah, and that's when the degree became materials science, and it was, we started doing some interesting stuff with commercial lithium-ion cells. So taking the likes of an 18650 out of a Tesla Model S, which is not designed to be opened at all, and finding a way to open it, stick some rods in it that have various instruments on them, and seal it back up again, and cycle it, and get the cell to pretend that nothing's happened. Because that way we can tell just how hard we can push existing chemistries and existing cells, without actually damaging them. Because at the moment we have very conservative limits on the way that we cycle cells, because we only really know what's going on with the temperature at the surface. We only know what's going on with the potential difference, the voltage of the full cell, not the individual potentials of the electrodes in isolation. You can't measure that on a commercial cell. With the tech that we had, we could. And there were some
Wow.
interesting results. So we know just how hard you could actually supercharge a Tesla.
So you intimately know the insides of a Tesla battery pack. You know intimately the insides of how batteries work. So in the next couple of minutes, could you give people a 50,000 view of how a standard battery works? And let's stick with lithium. Let's not go back and look at all these other different chemistries, because they're all slightly different. But the basic fundamentals of how a modern lithium-ion battery works.
Absolutely. So lithium ion, you have your two electrodes. You've got your positive and negative. The positive is called the cathode. The negative is called the anode. Now, ideally, the anode would just be pure lithium, because it's only lithium that takes part in the reaction, which I'll explain in a minute. But lithium has a tendency, when it's being charged back onto that negative electrode, across from the cathode to the anode, you find that if it's just a lithium foil, it starts to form branch-like growths. It doesn't play evenly. So you've got these so-called dendrites that start to grow across, and that can cause an internal short circuit where it actually touches the other electrode. So you don't want that. So what you have is graphite, so carbon, and the lithium pigeonholes itself in the layers of the graphite. So it's graphene that makes up graphite, and the lithium pigeonholes in there nice and safe. On the cathode, what you have is a lithium metal oxide. So people have heard of, for example, lithium cobalt oxide, the original chemistry that John Goodenough came up with, lithium iron phosphate, the cobalt-free chemistry that Professor Goodenough came up with. He's been quite active on the lithium-ion battery stuff, has he? There's generally some sort of variant of cobalt, nickel, manganese, aluminium, and that is the structure which lithium during discharge will go from the anode, the negative electrode, to the cathode, and it will intercalate. It will make itself at home in that structure. So it's all about lithium ions shuttling inside the cell from one side to the other. And then in the meantime, you've got the electrons that have been stripped off of those lithium atoms and then are recombined at the other end. They go through the external circuit. So in other words, they'll power the electric car that happens to be attached to the battery pack, because they cannot physically go through the inside of the cell itself, because the electrolyte and the separator, which is like a little polymer layer that separates the anode and the cathode, those are ionically conductive. So the lithium can go from one side to the other, but they are electrically insulating. So the actual electrons cannot move inside the cell, from one electrode to the other. They have to go the long way round through the external circuit.
And
And
that's
that's
really
just about the
important.
gist of it.
And that's really important to
Mm.
understand, because a lot of people think, oh, it's just electricity going from one. I mean, we all learn about batteries at school, right? We all learn that it goes one way, the circuit goes one way when you charge, and the other way when you discharge. But people don't actually think of things moving within the cell at all. They just think, I
Oh
put
yeah.
a wire on here and a wire on here, and the electricity flows. The magical juice just happens. You've alluded to some of the challenges with lithium-ion battery chemistry to this point, and there are many different problems. One of them is obviously that dendritic buildup that you talked about, and those dendrites can grow and actually cause short circuits, as you stated. The other issues are things caused by temperature and overheating. Because at a microscopic level, if you heat the insides of the cell up too much, that causes some problems, doesn't it?
Absolutely, yeah. So if a cell gets too hot, you're fundamentally looking at changing the chemistry that's going on. You will end up with the electrode materials physically starting to degrade. You'll end up with the electrolyte as well starting to physically degrade. That can end up with various decomposition compounds, which not only result in you losing the capacity of the cell because you've got less of the electrode structure for the lithium ions to actually house themselves in, and you've also probably lost a bit of lithium inventory there as well. The lithium will get consumed in these reactions, but you also end up with gassing of the electrolyte, which should be liquid, but obviously starts to gas as it decomposes. So if you end up with like a pouch cell like you get in a mobile phone, if you have a really dodgy mobile phone battery that was like an or some sort of El Cheapo electronic device that was bought off of Amazon, then you could find that if you've been hammering it, that and then you open the back of the case up, the pouch, which used to be flat, will be quite swollen, and that's gassing of the electrolyte. Don't pop it with a pin; that's a bad idea. But yeah, actually, this is where it gets interesting. It's surprisingly difficult to blow a lithium-ion cell up, and trust me, I have tried on numerous occasions. One of my former jobs at WMG, Warwick Manufacturing Group, a huge industrial academic kind of hybrid of a department at University of Warwick that does everything to do with not just electric vehicles, but vehicles in general. However, EVs are obviously all the rage, so there's a lot of battery research going on there. And they have some purpose-built abuse chambers to test things to destruction. And the Royal Christmas lectures they do on the BBC every year, they were supporting this on the battery one by showing you what goes wrong when what happens when a battery goes very wrong. And they did a few test runs of it by drilling into a big, like automotive scale pouch cell. And they tried it once and nothing happened. They were like, okay, we'll try really charging it to its absolute maximum voltage next time. Nothing happened. And then they had to properly overcharge it and heat it up and all this. And eventually they got it to catch fire.
Right.
But that's a complete digression, but just actually the safety point, you have to do something really wrong to get them to catch fire. It's quite interesting.
It's funny because different chemistries have a different propensity to catch fire. Nickel metal hydride obviously being one that is a little bit more likely to do bad things, as I discovered once. I built a plug-in Prius myself, and I had a battery pack that I overcharged. I had 3 battery packs in parallel, and one of the strings, one of the cells had shorted and reached the end of its life. It had shorted, and that caused that voltage on that cell, on that pack, to be lower than the others. And so my charging circuit, it's my own fault because I didn't design it to have one charger per string. I had one charger working across the parallel pack, was viewing the voltage as not being quite right, and it was just pushing current in until the car exploded. All the batteries exploded.
Unlucky. Yeah.
It was fun. It was fun. But again, we're digressing. With as a point, talking about your lithium-ion cells, I know we haven't got to Goodenough and his glass battery yet, and we're 10 minutes in, 15 minutes in. But it's important to note that even though these lithium-ion batteries are really robust, the reason why car companies like Audi, Tesla, Nissan, all these other companies have pretty strict rules over when the battery is considered fully charged and when it's empty, and how quickly the battery can fast charge. These are all designed to ensure that the batteries have a long life, not necessarily for any other reason, right?
Absolutely. In fact, a good example of that is, well, first of all, we should point out that if you look at the manufacturer's specification sheet for a given lithium-ion cell, take, for example, the ones that are in Tesla Model S, the Panasonic 18650s. Chances are the maximum voltage will be stipulated about 4.2 volts, the minimum voltage about 2.5. That doesn't mean that the car is going to charge them all the way up to 4.2 and down to 2.5 volts. They'll probably block off a few percent of the capacity at the upper end and the lower end of the capacity, the so-called state of charge buffers. And that, as you just pointed out, the lower SOC buffer helps to protect against over discharge if the vehicle's left for too long. The upper SOC buffer helps to protect against degradation associated with leaving a cell at fully charged for too long. The electrolyte starts to degrade against the high potential of the cathode. You compare that, though, with the battery in your smartphone that you leave plugged in most of the time, or your laptop that you leave plugged in most of the time. Not only are there not really any SOC buffers in consumer electronics, because, planned obsolescence, and also just in search of that tiny few minutes more runtime, some manufacturers of consumer electronics actually start to get a bit dodgy and overcharge the cells. So I've heard of some smartphones that go up to 4.3 volts instead of 4.2, all in search of a few extra minutes runtime, but at great expense of increased degradation. And that means that's why part of the reason why your phone battery dies after 2 or 3 years, but a typical EV battery's got at least a decade's life on it. And that's before it reaches, say, 80% of its original capacity. And with EV batteries being as big as they are now, that's still well into the hundreds of miles of range.
Right. So let's talk. I mean, that's a really good point. So thank you for making that, because a lot of people go, well, my smartphone runs out really quickly, so why should I buy an electric car? And that's a really good kind of indication that they're treated differently. They're engineered differently, and therefore the batteries will have a different lifespan. So let's turn our attention now. We've covered kind of the basics. We've covered where we are. Let's turn our attention now to Professor Goodenough and also Professor Braga. And there were some other researchers as well, I think, who were working on this project. I apologize, I don't have their names, but Goodenough and Braga are the two that I know. And they've come up with a new solid state glass electrolytic battery. So let's take that long name and let's break it down. Solid state glass electrolytic. So let's start with the first bit. What's a solid state battery?
So solid state, if we compare to a conventional lithium-ion battery, where you've got a liquid electrolyte that is soaking both of the electrodes, and then you've got a separator that, as I said before, is electrically insulating but ionically conductive, allows the lithium ions across. What we do with solid state is we remove the liquid electrolyte and the separator and replace it with a solid electrolyte. So something which is ionically conductive, allows the lithium through, electrically insulating, does not allow the electrons through, and that means that you basically have a 2-in-1 electrolyte and separator. So you've removed a component and you've arguably increased the safety as well.
And so the solid states have some benefits, don't they, over the lithium-ion chemistry, the WEPS chemistry that we use today, when it comes to long life. Tell us about that.
Yeah, so I mean, the other advantages, as we've already covered, are reduced costs because you've removed some components. You've got your increased safety because there's less flammable material in there. The liquid electrolyte has been removed. But from a safety perspective, solid state electrolytes are perceived as being dendrite proof. Now, it's actually more a case of dendrite resistant, but it's a heck of a lot harder for lithium, which is a reasonably soft metal anyway, to form those dendrite branches that would be hard enough to puncture through a solid electrolyte in comparison to a really thin layer of polymer. So I mean, the chances of an internal short circuit are greatly decreased, and that's where you can start to remove the carbon from the anode, which is used to safely house the lithium, and go back to using lithium foil, pure lithium foil. And that means that the anode is made entirely of material that takes part in the reaction, in other words, active material. And that's vastly improving the energy density of the cell even more, because instead of having 6 carbon atoms just to store 1 lithium ion, it's a very bulky way of doing it. You've now got lithium ions galore, and you can just have a really thin layer of them. And that means that you're looking at substantial increases in energy density, reductions in weight, and resultant improvements in performance.
So let's put aside here, because you just used a term that I know a lot of people may not know, energy density. While we're there, let's talk about energy density, power density, when and how it pertains to a battery pack. Because in this case, the solid state glass battery is promising a much higher energy density, and I think it's also promising a higher power density as well, right?
Yes, it does. It depends very much on the flavor of it, but we can cover that at the time. There's different variants of solid state, and there's kind of hybrids between them. But looking at energy density, there's 2 ways of looking at energy density, and it's all to do with how much capacity, how much energy you can squeeze in to a certain space or weight. So you've got gravimetric energy density, which is watt hours per kilogram. In other words, how much energy can you get for a given weighted battery? That you might think would be really useful for measuring for electric vehicles, but actually electric vehicles are more worried about the space that they can fit into. So that's volumetric energy density, which is watt hours per litre, because the litre is, of course, a defined unit and of volume. So that way, you've got a much better idea of how many watt hours you could squeeze into the vehicle. A particular chemistry may be lighter or heavier, but the important thing is if it's got higher volumetric energy density, then you're going to be able to squeeze more kilowatt hours into the same space in an electric vehicle.
Right.
As a good example, BMW, the i3 which has always used the exact same physical size of battery pack, has doubled its volumetric energy density in the space of 6 years.
Wow. I did that, and that's why the batteries have suddenly got higher capacity and can go further per charge. While we're on the subject of energy density, obviously let's talk through the logic here. Now there are certain types of battery chemistry. I know it's one you've worked on, lithium air, and there's also aluminium air. Both of those technologies are kind of quirky because they use the air that we breathe as part of the chemical reaction process, and that means there's less stuff inside the actual physical battery, and that's how they can store a lot more energy, both gravimetrically and by volume. And the same is kind of true here with the Goodenough Braga glass solid state battery, because as you've said, you remove stuff from that battery chemistry because you don't need the carbon, you don't need the separator, you don't need the liquid electrolyte. You replace those with a solid electrolyte. That means there's less physical stuff inside the battery, which means for the same given volume, you can put more of the battery goodness in. And that's why they've got a higher energy density. Is that a good kind of logic?
Correct. Yeah. So it's a fair way of looking at it. You've got 2 different ways you can go with it. You can either, as you've said, you can have the same physical size of battery pack and you can ram more kilowatt hours into it, considerably more, double, triple, quadruple the amount. But then the other way of doing it is you can reduce the amount of space that is dedicated to the battery pack, and you can reduce the weight of the vehicle, which again will improve range in its own way. And will reduce tire wear, which to be honest on EVs is not bad at all. They're very gentle on their tires, but again, it's making the vehicle even more efficient. So that's one advantage. Then aerospace is a different matter altogether because
I was just going to go there.
We're interested in. Yeah. I mean, you can stuff the wings of an airplane with batteries. Just any which way you can put the batteries in. They're not too bothered about volumetric energy density. You might think they would be, but they're not. It's gravimetric energy density. Is this aircraft going to be light enough to get off the ground? And the golden figure that keeps being quoted by industry experts is 400 watt hours per kilogram gravimetric energy density is when electric flight's really going to take off. That said, we've already got electric aircraft out there, small
Yeah.
electric aircraft, but that are capable of an hour or two's flight time. There's already plenty of use for that. That's not to be sniffed at. But
And
once you
aren't
get that
lithium
400,
at
it's
that
definitely.
point now? Isn't lithium getting to that 400 watt hours per kilogram at the moment?
To be honest, we're nearer 250-ish
Right.
at present. And that's, you might be getting a bit onto sort of 270, 280 with some of the really cutting edge stuff that's becoming commercially available. But that's at cell level. And then once you factor in the cooling system, once you factor in the bus bars to connect all the cells together, basically turning it from a cell into a pack, everything that you've just added is weight, and that's going to be this is not active material not taking part in the reaction, and that means that the pack level gravimetric energy density is decreased. So that's something that you need to try and factor in on these calculations. And you want to, if you're designing something for an aircraft, you want it to be as skeletal a pack design as possible and use as lightweight a material as you can get away with.
So let's now look at the Goodenough Braga battery. So we've covered that it uses less materials, so it's going to have a higher energy density. I don't think we've touched on power density yet, but power density is basically how much power you could instantaneously pull out of the battery, right? For a given moment in time. And we've got this fantastic battery that's been in the lab, that's proven itself in the lab. And the thing that everybody wants to know is, why don't we have it now? Why isn't it here yet? And what are the challenges to bringing it to market? So we've had people saying, oh, the Goodenough battery isn't real. We've had people saying, well, if it was real, Tesla would be investing in it, or it would be in a car by now. The reason kind of behind me reaching out and saying, hey, Ewan, I want to do this video is because I want to talk about the commercialization process. You've got something that works in a lab. You need to make it into a production line. We've currently got, I think it's Hydro-Quebec in Canada, has started investing in this technology. They are now looking and researching ways of going from the lab to the production line. But I want you to talk us through that and lay out some of the challenges that exist between where Goodenough battery is now and where it needs to be before we see it in an electric vehicle.
Absolutely. So as you've alluded to, it's not just the Goodenough battery that this applies to. This applies to any novel cell chemistry, and that includes numerous variants of solid-state battery that are under development at the moment from the likes of Toyota, from the likes of Dyson, Samsung. There are loads of different companies who are working on solid-state tech and research groups who are working on solid-state tech as well. So typically, you'll do a proof of concept first of all, and that's what we have with the Braga and Goodenough papers. So you'll develop very small cells, very small capacities, possibly in like a coin cell format, similar to what's in the back of your watch, that sort of idea, or in your car key. That's just probably going to be one layer of cathode and one layer of anode slapped together with obviously the novel electrolyte in the middle. That's all well and good. They will then be running that for a handful of cycles in comparison to the lifespan of an EV battery, a typical lithium-ion battery. I would be disappointed if a commercial lithium-ion cell didn't achieve a realistic 1,000 cycles without dropping below 80% of its original capacity. With many proof of concept chemistries, they'll run them for, say, 100 cycles, just to say, look, this worked. It didn't immediately fall to bits. Still more work to be done, though. The other thing that you need to consider is the so-called C rate that is applied when they're cycling this. The C rate is a measure of the current that is being drawn from or charged to the cell with respect to its capacity. So it's current over capacity. To put that into perspective, if you have a little pouch cell that's actually 1 ampere hour is incredibly generous for a pouch cell. It would be considerably less than that. But for the sake of argument, a 1 ampere hour cell, and you were running that at 2 amps, that's 2 over 1, that's 2C. And the inverse of that is the number of hours it would take to fully charge or fully discharge it, so half an hour. Likewise, if you were to charge or discharge it at half an amp, then that's 0.5C or 2 hours to fully charge or discharge it.
Right.
The C rates that some of these experimental cells are run at, not least the very latest Braga Goodenough cell, where we were talking, I can't remember the exact C rate, but it was very, very low. In an electric vehicle, let me have a think about what the typical C rates are you would encounter. 2C during rapid charging, and that includes most Teslas with supercharging. In fact, the likes of a Model S85 on a supercharger is probably not really going to top 1.5C, so it's quite an easy life.
So let's just pause here, because I just think it's really important with the C rate to talk about the fact that even though the C rate may be low, it doesn't necessarily mean that the car charges slowly, because of the ways that you can interconnect the cells within the battery pack. Now, Tesla gets around this low C rate by arranging the batteries in bricks in parallel and then in series. And so therefore, when it's dumping a high current into the battery pack, it's not dumping a high current into one cell. It's dumping a high current into strings and strings of parallel cells, right?
Absolutely, yeah. It's really not that scary to look at when you're looking at charging speeds in kilowatts of a supercharger or a rapid charger, quick charger, whatever you may call them. And you don't want to be looking at the absolute figure of, say, 50, 100, 150 kilowatts and thinking, oh my goodness, that's going to fry this one individual cell, because there are hundreds or potentially thousands of those individual cells that make up the battery pack in parallel, as you've just said, or, well, indeed in series as well, to get the voltage right. So ultimately, to look at the C rate, don't look at it from the cell level perspective in an EV, look at it from the pack level.
Right.
So, an 85 kilowatt hour Tesla charging at 120 kilowatts on a supercharger's, about 1.5 C off the top of my head. So, it's really not that scary. In fact, a Nissan Leaf 24 kilowatt hour charging at 50 kilowatts will be subjected to a higher C rate than the 85 kilowatt hour Model S. That's if the Leaf is feeling particularly frisky and up for 50 kilowatts. It's not always, but
not always.
if the battery's nice and toasty, then it's up for it. But so it's actually not that scary. The important thing is, though, that that's the sort of C rates that you'd be looking at in rapid charging. When you're cruising along on the road, you're probably looking about 0.1, 0.2 C. It's not much, but it's, that's the sort of figures you're looking at. When you're testing really experimental cell chemistries in the lab, it tends to be maybe 100th of that.
All right.
Sometimes even less. And in fact, it was really, really low C rates, like loads of zeros after the decimal point C, that were used in the latest Goodenough Braga study. I couldn't tell you the exact figure off the top of my head, but it was a very low rate.
So if it's charging... Sorry, carry on.
It's just that that's not immediately relevant to electric vehicles. It's still, it needs to be ramped up. It needs to go on to the next stage.
So getting it from the lab where it is at the moment, which is, we've got this chemistry that we think is going to use less material, is going to be cheaper to make, is going to have a higher energy density, we hope has a good lifespan. It's got a bit of a low charge rate at the moment, so the next step for them is to increase the charge rate and see how the battery responds, right?
Absolutely. So, you've got your proof of concept chemistry. You want to prove that when it's barely tickled, it doesn't fall apart. That's where you get your first paper and you go, look, in theory, this could potentially be really good at some point. Then what you do is, as you said, you crank up the current a bit. And if it starts to fall to bits, then you go back to the drawing board and you try to tweak the electrodes or electrolyte so that it can support a more commercially relevant C rate. That's not to say there are not very low C rate applications, but for maximum global benefit, you want to be ramping that up a bit. Now, and once you've cracked that,
do you know where they are at the moment with that technology? Do you know where they are in that process at the moment?
With Goodenough Braga, at the moment, it's still the very low C rate. Certainly from what we've seen with the latest publication, with the latest, most extremely novel chemistry that they've developed. With solid state in general, there has been an indication that you can get some very good C rates out of it. So solid state, there have been a couple of improvements by various different research groups, whether academic or industrial, over the past few years. One is they've managed to bring down the operating temperature to about room temperature, maybe slightly less, so you don't have to heat the cells up to run them. It will actually give you, decent performance at the sort of ambient conditions that you would have when operating an electric vehicle in most environments. The other thing is that, as I said, they've managed to improve the C rates. So there's two different variants of solid electrolyte, two main families. So you've got your ceramic or glass ceramic, which supports, in theory, a very high C rate. It's very ionically conductive for lithium. The downside is that it's brittle. So if you were to take that on an old brick road or something, the battery would shake itself to bits. So that needs a bit more flexibility. That's where polymer solid-state electrolytes come in. They're very flexible. They're quite forgiving on quite a tough environment with lots of vibration and shock. But the ionic conductivity of lithium is much lower, so the C rates are lower. So some research groups have developed ceramic polymer hybrids that have the kind of best of both worlds.
Okay, cool. So this Braga Goodenough battery, is that in the second group?
So this is a glass electrolyte, and from what I've seen of it, I'm not going to profess to know a great deal. There's, to be honest, a lot of it is behind paywalls, and when you leave academia and go into industry, you just have to kind of look from the outside, or ask one of your colleagues nicely, former colleagues nicely, to wing a paper over to you. But yeah, from what I understand, they're going down the kind of ceramic-y, glassy route,
right.
Like a particularly novel version of the kind of ceramic family. I haven't seen any mention of polymer. I will happily stand corrected if the very latest one does have that, though.
So after they've done, obviously, their capacity testing, they've done their charging testing, it sounds then that they have to throw in some physical, mechanical testing of the battery to make sure it doesn't fall apart. And then do they then have to do things like the puncture testing and stuff like that?
Oh yeah. I mean, we've actually kind of skipped a few steps in between. So you've started off with your tiny wee coin cell. You then build up to a kind of small commercial format, whether it's a pouch cell or similar to the size of one that you would find in a phone, or a cylindrical cell like an 18650 you'd find in a Tesla Model S. With that comes multiple stacks of electrodes. So you've got multiple layers of cathode and anode within the same cell. And then if you have any expansion and contraction during cycling, as the physical properties of the electrodes change, you may find that the cell starts to shake itself to bits, so actually physically crack itself to pieces, which you may not have seen or picked up quite as well in a coin cell with just one layer each. So that's another consideration that has to be taken in. All the while, you're also trying to up the C rate to something that's a bit more commercially relevant. Then you're starting to look at the various abuse procedures. So you want to find the true limit of these cells. You start seeing what temperature can these run at in terms of maximum and minimum. What performance can I get in, Saharan temperatures? What performance can I get if it was anchorage in the middle of winter? Turns out with solid state, actually, that some of the leading examples are pretty good in both examples. But then, as you said, you have your nail penetration test, where you deliberately charge the cell up, maybe heat it up for good measure, just because heat means extra reactivity and or extra speed of reaction, and then jam a nail through it, which is going to internally short all of the electrodes. So there's a direct electrical pathway without having to power an electric car and go around an external circuit. How does the cell react to that? Solid state seems to be a bit more forgiving because, as I said previously, the electrolytes are generally not flammable, whereas a conventional lithium-ion cell, the electrolyte is flammable, but only when provoked. So again, it's not that scary, but still.
So how long is this going to take time-wise? I mean, I guess how long is a piece of string, right? It's one of those questions.
Absolutely. You may think that you've solved all of the issues with the chemistry that you were aware of initially. Then it turns out that a process that you thought was the bottleneck you had to overcome was being caused by something else. And then you have to kind of go back a step to move forwards. And, it's it can be frustrating, but then you learn more about the chemistry at the same time, and then that iterative process does gradually speed up the development. With solid state, this episode is going to age well. I predict that with the amount of teams who are working on this, including big, industrial names like Samsung and so on, realistically, you could start to look at solid state coming online in electric vehicles that are available to buy between 2025 and 2030.
Right.
There's already been so much good progress that has been made, including the fact that there are actually variants of solid state lithium cells already on the market. There's a company across in the States, I think they are actually called Solid Power or Solid State Power, something to that effect. I've chatted to them at the big battery show they have at Detroit every year. Great show, by the way. But they've actually got small pouch solid state or variants of solid state lithium cells, which are currently being sold to the drone market, but which they are gradually scaling up to sell to electromobility, including electric vehicles. So we'll see how quickly that happens, but there are already commercially available examples of solid state.
So I've seen on Amazon, you can buy these little solid state booster batteries for your phone, your laptop, whatever. And they are able to dump a lot of power out in a very short period of time, which is why they can charge your laptop. But the thing they can't do is charge up very quickly. And so I've seen, some of these technologies coming to market, and I suspect, like you say, they probably are some kind of hybrid solid state technology. So they use some elements from solid state, but maybe some elements from more traditional established chemistry bands. So the Goodenough Braga battery, we know that Helena Braga is in Spain. Is she? She's based
Portugal,
in Spain?
I think.
Portugal. I do apologize. She's based in Portugal. Goodenough.
Don't want to get that wrong.
No, both wonderful countries. In case I've got Spaniards and Portuguese watching. Actually, I prefer Portugal, but we shouldn't say that.
Have we mentioned Catalonia yet?
Yeah, I love the country of Portugal. I've been lucky enough to go on a couple of test drives there. But Helena Braga is in Portugal, and John Goodenough is in Texas. And so there's a lot of collaboration across the world on this technology, as you've pointed out. The question I have for you related to that is, at what point does a chemistry go from being, we've met at a symposium. This is how I imagine it. You meet someone at a symposium who is working on a similar technology to you. You agree to collaborate. Maybe your university signs off on it and you've got a collaboration going. At what point does it cease being a university-funded project? Because let's not pretend that they just get money given to them, because they don't. They have to fund these projects, so they have to make the case to their academic institutions initially to fund the research. But at what point do people like Professor Goodenough and Professor Braga have to then start turning into a business person and say, hey, we need money from commercial entities to research it? How does that actually work?
It's an interesting one, because there's so much funding available within the energy storage sector right now that, depending on the country in which you are based, particularly the UK I'm thinking of here, the willingness of that government to try and lead the electromobility revolution means that, in theory, there's so much funding out there for battery research right now, they could just keep going. But ultimately, there comes a point when your tech has reached that technological maturity stage where industry has obviously been watching from the wings and goes, I want to get my hands on that. So, you've got the likes of Jeff Dan's research group that works exclusively for Tesla now, I believe. Tesla now fund them because they're aware that Jeff Dan's group specializes in tweaking reasonably conventional lithium-ion chemistry, but tweaking it really well. You look again at the other options that are out there, including if academics have a bit of an entrepreneurial flair and enough confidence in their creation, they can have a spin-off company which will go off and start trying to manufacture this. I've seen quite a few startups in the battery sector myself, whether it's to do with battery management, whether it's to do with the software side of things, or hardware, or whether it's to do with actually manufacturing cells. Sometimes they will go and get some government funding to set up a business, standalone business, which then has the production lines to actually make this. So yeah, I mean, it's difficult to put my finger on exactly when Professors Goodenough and Braga would go to the kind of commercial stage, but I get a feeling that it's more likely that industry is going to come to them. And indeed, Hydro-Quebec have already shown
Right.
interest in their latest, most novel, furthest away from commercial readiness technology. That's a very bold move from Hydro-Quebec. But certainly some of their more sort of conventional solid state tech, I wouldn't be surprised if, having managed to produce some automotive scale prototypes that survive a few thousand cycles at even just 2C, something like that. Heck, 1C is enough to kind of prove the credibility. That's when you would definitely get the likes of BMW, of Toyota, of the big OEMs, the big original equipment manufacturers out there, saying, we want to talk exclusivity, we want to buy your tech, or we want to buy your research group. We want you to work just for us now.
Right. And obviously at that point, then there becomes a decision whether the original academics who developed that battery, whether they license that battery technology, whether they allow themselves to go and work for that. And it's different with each academic, right? Some academics go,
True.
great, I'll come with you, I'll help set this up. I'm done with academia. I'm just going to work for you and do this. Other academics will go, actually, I really enjoy, maybe they've got tenure at their university or whatever. I really enjoy working here. I'm willing to consult with you on this project, but you need to get somebody else in to lead the project. So there are a lot of questions up in the air at the moment when it comes to the Goodenough and the Braga battery. We should point out here that, as I said earlier in our chat, I did reach out to the University of, it's A&M, I think, Texas, and say, hey, can I interview Professor Goodenough? I didn't get anything back. We did try a couple of times. I'm not that kind of person to push it to the point that, you know, they block my emails. I'm hoping at some point in the future, maybe I can interview either Professor Braga or Professor Goodenough about this battery specifically. And as you've pointed out, Ewan, although you are in the battery industry and that is your profession, you're not privy to the internal workings of this cell to be as intimately familiar with it as the projects that you're working on, and that's totally normal in the battery world.
Yeah, and on that note, I very much look forward to Professors Goodenough and Braga piece by piece picking apart this very video in their interview with you, because it's all a good learning experience for everyone involved. But yeah, I mean, obviously there's been a lot of controversy around the kind of the most revolutionary latest version of the solid state cell. To be honest, I'm going to take the kind of the Switzerland stance on this. I'm going to be politically neutral. I'm going to stay out of it. But yeah, in terms of the paper before, with the solid state high performance cell that they came up with, that definitely does have promise, and I've seen enough developments in solid state from other research groups to know that there's definite progress being made here.
Something we should definitely reiterate is they've come up with a series of different chemistries that it's like an iterative process, and they think that this one is better than the previous one. And obviously, as you've also noted, the battery industry there's so much money in it right now. If you come up with a working prototype, someone is going to want to pay you, or at least talk to you about extending that out to the next logical step. Which brings me kind of to tie this with a nice little bow. Let's just throw a bone out to some of the new chemistries that are coming online that we're more likely to see in EVs next year, the year after that. We know that Jeff Dahn, obviously, we've mentioned him. He and a team of researchers are now working exclusively for Tesla. They've come up with some new battery chemistries that will be going into what we think is going to be Tesla's in-house cell production process. Now, At CES this year, I can't remember if it was myself or Kate. No, it was Kate. Kate Warden-Elliott interviewed one of the PR folks at Panasonic to talk about their partnership with Tesla, among other things. She did ask them a very direct couple of questions about how are things going at Gigafactory, what's the relationship like, and they were skillfully avoided. The questions were skillfully unanswered or diverted, and all of the indications are that Panasonic is struggling to make the cells that Tesla needs at Gigafactory. There's a high failure rate of those cells in the production line. So each of the cells are examined and tested, or a certain number of those samples are examined. A lot of those cells are being returned and not making it into battery packs because there's quite a lot of errors in the manufacturing process. I don't want to speak to that directly because, again, I don't know. This is all information that I've heard, we've seen discussed publicly. And Tesla is making all of the right signs and all of the right motions that it's going to be producing its own cell. It's going to say goodbye to Panasonic in the long term. We've got the battery investor day that Elon Musk has been promising us probably this month. What are you expecting to see there? Are you expecting to see a Jeff Dahn cell that is then ready to go into series production?
I'm expecting to see one eventually. I wouldn't be surprised if they're holding back and doing further tests. There could be like the most subtle variant of Jeff Dahn's cell that is ready to go in there. There's definitely been improvements in longevity through additives in the electrolyte. So, just adding extra salts or chemicals in there, which either sacrifice themselves when there's some sort of degradation reaction that would otherwise take place, or help to prevent that taking place in the first place. That's a good bit of progress. But my favorite thing that Jeff Dahn's group's done recently is they looked at the nickel cobalt aluminium oxide chemistry, which Tesla use. Actually, it's almost exclusively Tesla that use it in the EV world. So they kind of stand out for that reason. Electrochemists had assumed for years now that the cobalt was required for thermal stability, that otherwise, if the battery got too hot, it would just fall apart. They looked at this in more detail, and it turns out that the cobalt's just in there for the ride. So cobalt, which is the one that everyone guilt trips you about if you're from an EV background,
right?
Like, oh, cobalt's unethical, blah blah blah. Some valid points, some not. But not only is the amount of cobalt in NCA, particularly Tesla's variant of NCA, negligible in comparison to what's in a smartphone that's lithium cobalt oxide, which is the old school chemistry still being used today. What you've also got now is the possibility to remove that cobalt entirely and replace it with a much more sustainable, ethical, abundant metal. So that's really exciting from an electrochemistry perspective, because that's just blowing a hole in what we thought we knew, and it's actually a really good news story. So I reckon that's going to be coming soon. There's definitely going to be an increase in the replacement of graphite anodes with an increasing amount of silicon, because silicon can store a lot more lithium than graphite can.
Right.
The problem with silicon is that it expands and contracts up to 25 times its original size during cycling, so it mechanically breaks the cell apart. One of the ways around this is to have just a tiny kind of sprinkling of silicon fairy dust in a conventional cell. But we're starting to see more and more silicon being introduced and less and less, well, more and more graphite being removed. One of the best examples I've seen of this is something, I don't know if it's ready for commercialization yet, but it sounds very promising. A silicon anode with what I would describe as a graphene corset around the silicon, which holds it in place as it's trying to expand and it can't, and it holds it there so it's nice and safe and you'll get a long cycle life out of it. And that's, again, really vastly improved energy density as well. That's a big improvement, which I think we're going to see in a lot of electric vehicles, not just Tesla, but loads of EVs will see that. Obviously, we'll hopefully see solid state eventually, but in terms of other chemistries that are quite interesting, for the entry-level market, there's sodium-ion, which is less energy dense than lithium because sodium is larger and heavier than lithium, but has a couple of advantages. Not only is it cheaper, arguably more sustainable materials. You're talking about, I think it's an estimated 30% cost reduction, but also you can safely and reversibly fully discharge that cell down to 0 volts. You could short the terminals out with a resistor take it down to 0 volts, so there'd be no energy left in it, and you could ship it all the way around the world, fly it all the way around the world without having to have any, really uppity safety regulations. And
Huh.
it costs a lot of money to ship lithium-ion cells because of the safety regulations and the packaging they need. Whereas with sodium-ion, you could practically just chuck them in a suitcase and go, there you go, see you on the other side of the world. And that's a huge cost reduction in itself. Renault are very interested in sodium-ion, and it's being developed. One of the research groups or industries that's developing it is a really cool company up in the north coast of Scotland in Thurso, next to where the Dounreay power station used to be, called AGM. They're a great bunch up there, and they're developing this cutting edge chemistry. Lithium sulfur deserves a good shout as well. Aerospace are really interested in this one because the volumetric energy density is about the same as lithium ion. So, you'd be talking about the same size of capacity of battery pack within the same space, but the gravimetric energy density is much higher. And that means that electric flight could take off with lithium sulfur. Plus, sulfur is abundant and cheap.
Right.
There's still a couple of issues to overcome with the chemistry, including the polysulfide shuttle, which is a self-discharge reaction. But there's a company called Oxis who are developing, they've developed many, many prototypes, like industry scale pouch cells, yay size, that are like 500 watt hours per kilogram. I think they're up to now, and they're building a factory in Brazil to actually commercially produce these. So that's got to be coming soon, surely.
This sounds
Those
fantastic.
are
This really sounds exciting. I especially like the idea of a low cost battery, because obviously we know that Renault's really pushing the Dacia brand and obviously affordability. We are in a global economic crisis. If we're not in it now, we're going to be in about 2 or 3 weeks time, and it could last for the next 5 years before everybody's really back on their feet. And if there's a low cost battery coming in that can get people into electric cars, even if they're only electric cars with 150 miles to 200 mile range, and I know there are people watching this channel who say, no, it has to be a Tesla, it has to have 400 miles, I'm not interested in anything less. In North America, in Australia, and other countries, that might be the case. But lots of European countries, 150 miles of range is more than enough for average driving.
Oh, God, yeah.
And you have a Nissan Leaf. You did a wonderful series of road trip videos where you drove across Scotland in your Nissan Leaf to demonstrate the fact that you do not need a high mileage car to have fun, to make these kind of long distance trips. So an affordable, longer life battery that has 150 miles but maybe is a little bit heavier, I think that's going to be really very popular if it allows companies like Renault to save money in the process of production, but also lower the sticker price.
Oh, too right. And even if if we see the decline of the personal car because of a global recession, it's still important to have cheap and ethical and sustainable battery chemistries, which can be easily produced for public transport. Because even though I think we're going to see a lot more teleconferencing in the in the continuing on from now, we're still going to need to get some people from A to B, and again, online delivery vans and things like that, and drones. They're going to need batteries. So if we can make those batteries cheaper, and we can then increasingly decarbonize diesel fleets by switching them across to electric, and also we can increase fleets of novel delivery vehicles or whatever like e-bikes. E-bikes are properly taking off at the moment as well. So again, being able to reduce the cost of e-bike batteries and boost the range a bit, there's definitely advantages to it. This is not all in vain. There's plenty of use, and grid storage as well. We've not even covered grid storage. Sodium ion. Who cares about the energy density if you've got loads of space for shipping containers?
Right.
You can just stick them in there and balance the grid with them.
Ewan, thank you so much for joining me today. I suspect this is not going to be the last time that you join me on the channel. Thank you so much. I'm going to give you a chance to tell us what you're working on for Plug Live Television, and tell people where they can find out more.
Awesome, thank you. Well, at the moment, Plug Life Television has just launched a new sub-series. So there's a few different themes of shows that I do on it, covering various different battery or EV-related topics. And the latest one is What Barriers, which is talking about balancing the rapid charge to electric vehicles, talking about how we can balance everything that is required to shift an entire nation's cars across to electric. Now, I've decided to focus on home. It's talking about the UK market for this one, but equally the lessons can be applied to other nations as well. The first 3 episodes of that are on at the moment talk about balancing the grid, and you may be pleasantly surprised at just how easily the UK's 31.3 million 31.3 million cars could become 31.3 million electric cars without tripping the grid at all. Then we'll look at raw materials. We'll look at social mobility. Not everyone can afford a brand new shiny electric car. How can, there's the arguments about people being villainized because they can't afford one, and being forced into to poverty by having to go for an EV, that sort of idea. We'll look at that and we'll see how much truth there is in that argument. So basically how to balance it so that everyone wins is the kind of model of that, and then also looking at the data and seeing how plausible it all is. Fantastic. And you'll find us on YouTube at Plug Life Television, and also pluglifetelevision.co.uk.
Thank you so much, Ewan, for that. It has been a fantastic hour-long session. I hope you watched the video from start to finish, and I suspect I'll be getting Ewan back on in the future to talk about batteries, because he knows so much, and my mind is just swimming with all the datas right now. I hope that if you are back at work with the level 3 zone that's now in place in New Zealand, that you are staying safe. I hope that you and yours are well. We'll be back soon with more cool content for you all to enjoy. Don't forget to switch to New Zealand's only carboNZero certified renewable electricity supplier. I'll be back soon. Until then, ka kite. See you next time.